Okay, so thanks for having me. It's a pleasure to be back in Bonn. Okay, so I want to start by a brief discussion of hyperbolic three manifolds. Okay, hyperbolic three manifolds. So I should say that all of my manifolds will be closed and oriented. Okay, so we want to look at hyperbolic three manifolds. So the first question is, how do you make one? Okay, so I will give you a very simple-minded way of making a three manifold. So how about we take a surface? So we take a surface, closed and oriented, sigma. We're going to also choose a homeomorphism of the surface, and we wanted to preserve the orientation. Okay, so now we are going to take our surface, make it into a cylinder. Okay. Cylinder, and we're going to glue one end to the other via F. Okay, so formally the manifold is sigma times the interval, where we glue a point mod 0.0 to point, f of the point, comma 1. Okay, so now it's easy to convince yourself that this is indeed a three manifold. Okay, moreover, if F is a pseudo-Anosov mapping class, I will not tell you what these are, but if it is, then the manifold M is hyperbolic. Okay? So this is a construction of a hyperbolic three manifold. Now the definition, if M, a three manifold, comes from this construction, then it is fibered. Okay, so that's the definition of the word fibered. Okay, so now on the level of groups, what happens? So on the level of groups, we have the fundamental group of the three manifold. We have the fundamental group of the surface, which embeds. Here we are mapping onto the fundamental group of the circle. The fundamental group of the circle is Z. And this is an exact sequence. Okay? So that means that we can write pi1 of M in terms of representation. We take pi1 of the surface, we add in a stable letter, and now we act, right? So we're going to take an element from pi1 of the surface. We're going to hit it with T, well, we conjugate, and this guy is going to be f of x. Okay? What is f of x? So x is an element of the fundamental group, I should say, of the surface. So it's really a loop. If you hit a loop with a homeomorphism, you get another loop, so that's a well-defined element, except of course not, right? It's a well-defined conjugacy class, but it so happens that this construction doesn't depend on which. So you can modify this automorphism of pi1 of sigma by a conjugation. It doesn't change anything. Okay, so this makes sense what I wrote. Okay, so this is what the group level says. So now I want to introduce the concept of an ascending H&N extension. So a group G, which we can write as a subgroup H, a stable letter, and x t inverse t equals f of x, where, okay, so H was a subgroup, and now F is a monomorphism from H to itself. Such a group is an ascending H&N extension. Okay, and we write G equals H star F. Okay, so note that I do not require F to be an automorphism of H. It's just an injective map from H to itself, where homomorphism. Okay, so a couple of observations. Nope. Okay, Oh, did that happen? Oh, yeah, I see. Okay, now, yes, well. Okay, so, facts. So first fact, if you take a group which is a semi-direct product, then this is an ascending H&N extension. Okay, that's obvious because an automorphism is an injective map from the group to itself. Secondly, if you take such a group, I mean an ascending H&N extension, you get an obvious map onto Z. Okay, so I call it phi. This map has H in its kernel, and it takes the stable letter to the identity. Okay, so the identity is the generator, one of the generators of Z. Okay, so this, such an F, this is such a phi, this phi is the induced character of the H&N extension. Okay, so, of course I forgot about the important motivational result. So, talking about the fibering and hyperbolic free manifolds, one has to mention the theorem of Agel that every hyperbolic free manifold is virtually fibered. Okay, so up to finite index, all of them come from this simple-minded construction. Okay, so we've discussed the H&N extensions, and now we go into the BNS invariant. So, definition: the Bieri-Neumann-Strebel invariant, which I will abbreviate to BNS. Okay, so let us take G with a finite generating set. So G is a group. We take it with a finite gen set S. Okay, and we define sigma of G. This is the sigma invariant, the BNS invariant. It lives inside the first cohomology of G with R coefficients, take away 0. And we define this by saying that a character, phi, belongs to sigma G, if and only if the following is true. So we look at the induced subgraph of the Cayley graph of G with respect to S. Okay, the induced subgraph of Cayley graph spanned by all these vertices. So vertices correspond to elements of the group, right? So it's spanned by all the elements of the group which are taken to something non-negative by the character. Okay, so that makes sense. The character, an element in the first cohomology group, is just a homomorphism from the group to R. Some elements will be taken to non-negative guys. These form a subset of the vertex set of the Cayley graph, so we can look at the induced subgraph. Okay, so we add all the edges that have both endpoints in, and this guy is asked to be connected. Is connected. Okay, so this is the definition of the BNS invariant. Now, okay, I will leave it for you to stare at. Take the board. Okay, so this is the definition. Now, the definition has a problem, namely, it's not easy to verify. okay? Which element is in the sigma invariant and which is not. But there are some facts which are going to make our life a bit easier, because there are some characterizations. So fact one is that if we look at a character which takes our onto Z, then we can say that then phi lies in the sigma invariant. If and only if we can write, so if and only if we can find a finitely generated, very important, subgroup H inside G, and a monomorphism, okay, such that G is an ascending HNN extension over F, and phi is the induced character. So again, I stress H has to be finitely generated. If you don't assume that, you can always do it. Every character to Z has a kernel. You can write G as a semi-direct product of the kernel and Z. Okay, that's not good enough, right? Finitely generated. Okay, so this is the characterization. So in fact, the definition would be completely useless for us, and this is really what we want to focus on. Okay, so this is the sort of characterization that we care about. Okay, now second point. We know that if both phi and minus phi lie in sigma invariant, well, this is equivalent to saying that the kernel is finitely generated. Okay? One direction is easy, the other one is not. But okay, so theorem. So this was essentially proven by BMS, by Bieri-Neumann-Strebel in the original paper, except it required conjecture. So I will put Perelman in. And now we know that for a 3 manifold, M, we have, okay, so phi, a character from the fundamental group of the 3 manifold onto Z, lies in sigma of phi 1 of M, okay, if and only if M is fibered. Okay, and now if M is fibered, a particular fibration we choose gives us a way of writing the group as an H&N extension that this gives us the induced character. Okay, so I want this character to come from the fibration. M is fibered, and phi is the induced character. Okay, so this is a very nice characterization of the sigma invariance for 3 manifolds. Okay, so in particular, well, what also is true, it doesn't quite follow from this. Yes. That is true.
So it means it's automatically find minus phi.
That is true, and I was just about to write that. But what you say is true for characters going to Z, whereas the statement is also true for characters, general characters. So it doesn't quite follow from this, but almost, yeah. But I was just about to write it. So the second thing is that phi lies in, so any character now, phi lies in sigma G, if and only if minus phi lies in sigma G. Okay, this is special for 3 manifolds. So G is, of course, phi 1 of Can I generate the kernel? Well, but this is just the intersection of sigma G and minus sigma G. Right. So, I mean, it's spat out by this. So, yeah, okay. So, this was BNS. Okay. And now, right, so now we go to a more refined tool. So, the BNS invariant captures somehow the problem of fibration, okay? But if you fiber, you also, well, if your manifold is fibered, you also have the fiber. And you might want to know something about that, okay? So this is the next thing we're going to. So the more refined tool is the Thurston norm. So it's kind of similar in spirit, I would say, but, well, it gives you more information. So we start with a character from, again, we are looking at the 3 manifold. We start with a character going on to Z. And now what we want to look at is, so we define the Thurston norm of this character to be what? Okay, so first of all, maybe I'll start with this. We started with a map from pi1m to Z. That's in particular an element of the first cohomology, okay? But because we are looking at the 3 manifold, first cohomology is dual to second homology, okay? And elements of second homology are represented by surfaces in a manifold. So we are going to look at all sigma. Sigma is a surface inside M, dual to phi. Okay? So this is what we are going to look at. So now we have the sigmas. Now for each of these sigmas, we take essentially the Euler characteristic. I will explain what the symbol means in a second, but think of Euler characteristic, and then we take the minimum, okay? So what is this symbol? So chi minus of sigma, well, this is a sum, okay, over sigma i's, which lie in which are connected components of sigma, and we take, max, between 0 and minus the usual Euler characteristic of sigma I. Okay, so what do? We take our character, we look at some dual surface. The surface does not have to be connected, it comes with bits. We look at each bit, each connected component, and we check, is it a sphere? If yes, then we throw it away. Is it not a sphere? We calculate the Euler characteristic and take minus that, so to make it positive. Okay? And now we take the sum over our components, and we analyze this number. We now go through all possible dual surfaces, and we take the smallest. Okay? So we are trying to find the least complicated surface which is dual to our element. And if we find it, the Thurston norm just spits out the Euler characteristic. That's the definition. Okay? So now, okay, we need more space. Right. Okay, so now some facts. So I guess it's the theorem due to Thurston. Okay, so what did I define? So I gave you a map. I gave you a function which takes a character, a primitive character, taking pi1 m to z, and I associated a number. Okay, so the first thing that Thurston proved is that you can extend this to a map from the entire cohomology to the non-negatives. Okay, so that's, you just do it by continuity. Secondly, well, I will do them with dots. Secondly, I told you this is the Thurston norm, and in fact, this guy is a semi-norm. Okay, so this is already non-obvious, right? It's just some association to a character. I mean, you associate the number to a character. It doesn't have to have any properties, but it does. It's a semi-norm. Moreover, if M is hyperbolic, then this is actually a norm. Okay. Now, the unit ball. So if you have a norm on a vector space, you can look at the unit ball. So the unit ball of this norm is a finite-sided polytope. Okay, and that's not the end. So Right. The sigma invariant. This so it will in case when this is a norm it is. Yeah, otherwise not. It's an intersection of finitely many half spaces. So no, it's not compact. But okay, now the sigma invariant. So the sigma invariant of pi 1 of M is equal to the cone over some maximal open faces of the unit ball. The picture counts. Okay? What does it mean? Well, how about this was the unit ball of our Thurston norm. It's a finite-sided polytope, right? Now we look at the maximal open faces, but there are 6 maximal faces, 6 edges, and some of them will be special. Okay? Say these two. And the sigma invariant will be the cone over these. Okay, so these faces. Sorry? Symmetric. Okay, but so the picture is misleading, but at least it's okay. So it's not quite like that, but it's misleading, but only a bit. Right. Okay. So what else? We know that the Thurston norm of a character is. Okay, so let's start again. Let's suppose that M fibers, and the fiber is some particular surface. This fibration gives us a character, pi 1 to Z, and we know that the Thurston norm actually calculates the Euler characteristic of the kernel of this. Well, calculates the Euler characteristic minus of this slice. Okay. So if you fiber, then it spits out the correct thing. That's what you want. Okay, so this is the end on 3 manifolds, and now we move into something more relevant in this conference. So now the universal L2 torsion. Okay, the universal L2 torsion. This is due to Stefan Friedl and Lück. I will not really define it, but almost define it, I guess. Okay, so we take G, this is a group, with finite KG1. Okay, so it has to be of type F. We want it to be L2 acyclic and satisfy the idea conjecture. Okay, that's our setup. Now, if we have such a group, okay, so how about we give this guy a name? This is now called X. If we have such a group, then, well, what do we have? So we have a group, so we have the group ring. By passing to von Neumann algebra and then to the algebra of affiliated operators and taking the division closure, as we've seen before, we have an object, a ring, called DG. Okay? Now, because the Atiyah conjecture is satisfied, and because we have a finite classifying space, so we are torsion-free, this is a skew field, as we have seen before. Okay? So now why do I need it? I need it because we are now going to define a weak K1 group. Okay, so I need space for that. Okay, so the weak K1 group. Definition. Okay, it's a little lower. Lower, right. Weak K1 group. Okay, so what is that? So This guy is so this is an abelian group generated by weak isomorphisms between three ZG modules, by which I mean. So let's take a free ZG module. Let's map it to another free ZG module of the same rank. Let's take the ring homomorphism. Now, we know that ZG embeds into a skew field. So we can extend scalars. We extend scalars, and we obtain a map between two vector spaces. Okay? Now, F is a weak isomorphism if this guy is an isomorphism. Okay? So you should think of, kind of completing, right? So you have some matrix that's trying really hard to be an isomorphism, it's trying to be invertible, except you took a stupid ring. Okay? So you get rid of the stupid ring, you replace it with a skew field, and suddenly everything is nice and invertible. Okay, so that's a weak isomorphism. Such a weak isomorphism, so this is the object. This object. Yeah, right. If you tensor with L2, you get an. It's not enough to be dense, right? Is it? Ah, okay. I see. So yes, I see. Right. Okay. So now this object, this is a generator of the group. Okay. And now you have relations, and the relations are the usual K1 relations. Okay. If you know what they are, you just define the group. If you don't know, it's some abelian group. Okay. It's made of such things. I will not tell you what they are. So relations are the usual relations. Relations as usual. As usual for K1. Okay, now, here comes the black box. So, since we have this, we know that X is, right, so G is L2 acyclic, okay? So, if you have an acyclic group and you want to take the Betti numbers, you know they're all 0. But there's a more refined tool, the Whitehead torsion, okay? In our setup, we know that the L2 version of Betti numbers is 0. So we have the L2 version of Whitehead torsion, okay? So you proceed in exactly the same way as you do for Whitehead torsion. And defined exactly as well as Whitehead torsion. Whitehead. Torsion. We define the universal L2 torsion. Okay, which I will denote like that. It's a bad notation because it depends on the X we chose, but let's leave it like this, okay? Now, what is it? This is an element, and that's the only thing we need to know at this point, of this weak K1. Being an element of the weak K1 means that you can represent it by a ring morphism from ZG to the N to ZG to the N, which becomes invertible when you tensor with DG, okay? So that's what we have, right? So we have some ZG to some N, we don't know what N, doesn't matter. Okay, and this guy, well, there's some F, and this is exactly this, okay? But now again, we extend scalars. And we know that this guy is an isomorphism. Okay, let's also denote it by F. And this is an isomorphism. So now we have an isomorphism between vector spaces over skew fields. Now what can we do? Okay, so you have a matrix, an n by n matrix over a field. What's the best thing you can do? The best thing to do is to take the determinant, right? So we take the Dieudonné determinant. What's the Dieudonné determinant? Well, so we are not over a field, but a skew field. How do we normally compute a determinant of a matrix over a field? We do Gaussian elimination, okay? Dieudonné determinant does Gaussian elimination as well. Over a skew field, you can easily do it, okay? So you can convince yourself now that you can do Gaussian elimination over a skew field. So you do it, you get your matrix to be upper triangular, and you just take the product of the entries on the diagonal. That's the Dieudonné determinant, okay? So we just did it. We took the Dieudonné determinant of this object. Now, where does the determinant land? Well, since it's a good determinant, it better land in the field, right? Well, except of course it will not, because the problem is that in skew fields are not commutative, right? So if you take a matrix and you start performing things, you might accidentally invert two elements on the diagonal, for example. And then when you take the product, it's not the same element in this field. But it's almost this, okay? So what you do is you look at the group of units, which means you throw away 0, and you abelianize it. Okay, now it's well defined. But the good thing is, you can forget about it, okay? We are going to think about it as sitting inside the G. I don't care about that. That's not important. What is important? So there's one thing that there's one thing that Thomas didn't tell you about DG, interestingly enough. So what we didn't learn about DG in the previous talk is that DG itself is the Euler localization of what? Okay, so first I will write it of a group ring of G up F. So what is G up F? G up is the abelianization of G. F stands for free, so you threw away all the torsion. Okay? So G up F is the largest free abelian quotient of G, and K is the kernel. So we have the exact sequence like that. Okay? Okay, so now K is some group, so we can apply this deconstruction to it and we get something. Well, in fact, we get a skew field. This guy is a twisted group ring. Let's not worry about that. It's a group ring of this abelian group. And then you can localize at the zero divisors, at the non-zero divisors, rather. And what you get is DG, okay? So the bottom line from all this is that, and that's the only thing we care about, is that if you take the universal L2 torsion of your group, you take the diagonal determinant, you land in this DG, almost. This DG is the field of fractions of this ring, okay? So any element here can be written as a fraction of elements here, okay? This is an abelian thing. So this guy is just some fraction, P, Q inverse, okay? And these guys lie in some admittedly complicated group ring of an abelian, free abelian group, finite rank, okay? So that's an easy object. That's the idea. So we did all this black boxing, and we took some determinants, but we arrived at something that we have a hope of understanding now, okay? Some water. Okay, so now we wrote our universal L2 torsion as a fraction. And now we are only going to do easy things, okay, from now on. Nothing complicated will happen. So again, I'll just write it that G is some fraction. Okay, well, these guys lie inside some funny group ring of a free abelian group. Okay, so now if you have an element of a group ring and you don't understand the coefficients and you don't want to understand the coefficients, what you do is you take the support, okay? So we take P or Q and we look at the support. Now the support is just a subset of, well, of the free part of the homology, right? I just rewrote what G up F is in terms of homologies. But now, if you look at the homology with coefficients in Z and you take the free part, this guy sits inside this vector space, finite dimensional vector space, real vector space, okay? This is obvious. Now, we have a finite collection of points inside the vector space, well, inside the metric space. What do? Well, we define P, this is a capital P of little p, to be the convex hull of sup P inside the vector space. why not, right? I mean, you have a bunch of points, and you just define the convex Hana. That's P of P. Okay? So we took an element in this Fanny group ring, and we converted it to something very simple. It's a polytope in vector space, and R to the n. Now, a polytope, actually any subset, a polytope, P in H1 G induces a map NP, which takes us from first cohomology to 0 infinity. How does it do it? Well, okay, so NP is a map from first cohomology. So you feed it a character. You feed it a character and it's supposed to spit out a number. So how about we look at max over phi of A minus phi of B, where A and B are in P. Okay, what did it do? Some color. So what it did is had the polytope. We took a character. The character we are going to think of as giving us a direction inside this vector space. And now we are taking this polytope and we are flattening it onto this direction. Okay? This is the flattening. And this number just measures how thick this is. Nothing else. How thick you are with respect to a particular direction. Okay, so that's just a number. So now, what do we have? We have a fraction of two elements. So we started with P Q inverse. To this guy, we associate a pair of polytopes. Because we can. And to these, we associate the difference of these functions. Okay? And this, remember, is the universal L-torsion. Okay? To the universal L-torsion of the group, we associate it. What is it? It's a function. It's a function which takes elements from first cohomology to some real numbers. Okay? It's a function. But now the magic. So this is the theorem. Friedl and Lück. Okay, if G is pi 1 of a 3-manifold, then this map here, NPP minus NPQ, is the first norm. Okay? Why would it even be positive? That's the first norm. Okay, now, so this is all very nice, I think, but it has a use. So, I mean, why go to all this trouble just to redefine the object that we already had? Well, the point is that now, if we take G with finite KG1, which is L2 acyclic, and satisfies the Atiyah conjecture, and there's one more condition, unfortunately. You need the Whitehead group, the classical Whitehead group, to be 0 for reasons which I brushed under the carpet. But if that's satisfied, then you also have this universal L-torsion, which you can also write as PQ inverse. I mean, there's nothing about 3 manifolds. And you also get this funny function. And now you just define it to be the first norm. Okay? So all the yoga allows us to extend the definition of the first norm from 3 manifolds to admittedly much more general class of groups. Okay? I mean, they seem to satisfy a lot, but it's really not that bad. Yeah? It's many groups which satisfy that. Okay, so now it's time for something else. if my group has trivial abelianization, well, no, I mean, then everything sits in the kernel, right? I mean, dg is dk. So, I mean, if you want to pass to the polytopes, you didn't learn anything, right? Because the polytopes are just points. Okay, then it's useless. So studying it for groups with trivial abelianization is useless, yeah. But it's a lot like the BNS invariant, right? I mean, the BNS invariants, if you want to study them for groups which don't admit any characters, is pretty pointless. So, but fortunately for us, many interesting groups do have non-trivial abelianizations. I will get to a class of such interesting groups in a second. So first, I need a super theorem, a combination of 4 theorems, I think. So it's due to, okay, it will not be alphabetic, I think. So due to Lück, Waldhausen, all separate papers. I hope I didn't forget anything. So let G be an ascending H and N extension of a free group. Okay, and how about we take all these properties and call them star. Okay, so if G is such a group, then G satisfies star. Okay, so various parts of star are due to various people. They're all listed. Okay, now, so it means that our Thurston norm can be defined for free-by-cyclic groups. Okay, so free-by-cyclic groups are cousins of three-manifold groups, right? So they are related. Many of them are actually three-manifold groups. Well, maybe not many. Some of them are. Okay, but now here comes the theorem that is joint work with Florian Funke. And what did we prove? Let's check. So, maybe not the most important thing, but something that is kind of, I would say. So it turns out that the Thurston norm in this case is a semi-norm. Okay, so this is some sort of magic. I mean, there's absolutely no reason why it would be true. It's a difference of two functions, blah, 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 but it is a semi-norm. Okay, and well, that's. I should mention that the proof of this is based very much on a paper of Friedl and Lück. So it's very much the same. Yes. It's a semi-norm for this particular group. Yeah, on G, Fn, well, the ascending H and extension. Okay, since these are the groups we care about. Moreover, how much? Ooh. Okay, so that's the first theorem I can really say. Now, to mention another theorem, I have to introduce another concept, right? So let's go to Alexander norm. Okay, so if you take any finitely generated group, G, you can associate to it the Alexander polynomial. Polynomial delta G. Okay, this is an element in the group ring of GABF again. Now an integral group ring. So we have an element in the group ring of GABF. We know what to do. Yeah, I mean, what's the most obvious thing you can do? Of course, you take the support, the convex hull, and take the norm. I mean, what else, right? So we do that. So we have DG. We take the support. Well, we take the polytope construction, and we take the norm construction. Okay, this is a function from first cohomology to non-negative reals. Okay, and this guy is the Alexander norm. So this is the definition of the Alexander norm. Okay. Now, so this is actually an object that is, well, pretty old and important, especially for knots. But now what is interesting when you compare the Alexander norm and the Thurston norm is the theorem of Macmillan. So Macmillan says that if we have M, a three-manifold, with the first Betti number at least 2, then the Alexander norm is a lower bound for the Thurston norm. So this was actually an important result because the Thurston norm is very hard to compute, and the Alexander norm is much easier to compute, okay? Sometimes you only care about the lower bound, so this is the use of this. Secondly, if a character is fibered, by which again I mean that the manifold fibers and the induces character is phi, then the norms actually coincide. Okay? Now it's a result of Dunfield that in general they do not coincide. Okay? So note this is not an if and only if statement, right? For fibers they coincide, but there's no converse. Oops. But these guys in general are not the same. Okay, and now here comes another theorem which I proved with Florian. Oops. So it turns out that if you go away from the three-manifold setup and go to the free-by-cyclic setup, or ascendications and extensions for free groups, then the same is true. So take G, F, and F, where either n is 2 or F is polynomially growing unipotent automorphism. Why did I go to G's? All right. Okay, it's unipotent polynomially growing, right? Automorphism of Fn. Then, and we need this assumption on the Betti number. Then again, the Alexander norm is bounds the Thurston norm from below, and these guys are equal when phi is fibered. What does it mean? Well, so we are not in the three-manifold setup, so I have to define what fibered means, and fibered just means that the kernel is finitely general. Okay, so the theorem of Macmillan generalizes from three manifolds to a much more general class of groups, these ascendications and extensions. Unfortunately, we couldn't get it to work for all such groups, so we have these two restrictions: either n is at least 2, and then we allow any injective map F, or F is this special kind that I might get to discuss at the end. Okay, so this is the state of the art. Yeah, okay, yeah, so in spirit. In spirit, yeah. Yeah, right. So what I mean, okay, so it takes it away from this natural setup. That's what I mean. Okay, so now I also mentioned the BNS invariants, and there is a relationship. Okay, so there is a relationship between the universal L2 torsion and the BNS invariance. So again, this is Florian and myself. Setup is the same, so G is Fn F, where either n is 2 or F is UPG. We'll get there. Then the universal L2 torsion of G determines the BNS invariance. Now, okay, this is as vague a theorem as you will ever see, right? What does determine means? So I will explain it in detail for the UPG case, okay? So if we take, so let's first define what UPG is. Definition. So an automorphism of a free group is UPG if and only if we take any non-trivial element well, actually any element in Fn, the word length of f to the n x grows at most polynomially with n. So that's the polynomially growing part. And U for unipotent means that if you take the natural map from auth Fn to GL and Z by abelianizing the group, you take your f and you just map it here to some whatever f bar. This guy, f bar, is supposed to be unipotent. I should say every polynomially growing automorphism has a power which is a UPG. Okay, so you are free to think of polynomially growing automorphisms, which are, well, a nice class. Now, for such guys, if we compute this distortion, it turns out is that in this case, rho u to g is actually just a single p. Okay, we don't have to take a denominator. It just so happens. But this makes our life a bit easier because then the polytope we look at is just a single polytope, right? So now we have some polytope. In fact, we know what this polytope is. It's always a parallelotope. Okay, so it's a cube essentially. Okay, that's what it is. And now, how does it control the BNS invariant? So if you take any character phi. Well, started. As I said before, a character gives you a direction in this vector space where this polytope lives. So how about we take this direction? Okay. Now, if you have such a direction, well, just phi, you look at the face of the polytope, which has minimal value under phi. Okay. In this particular example, this is going to be this face. Okay. Well, I mean, it's not a maximal dimensional face, but it's some face. Now, let's take such a guy. And now assume that we take another. So for every other character, psi, with the same minimal phase on our polytope, we have that phi lies in sigma g if and only if psi does the same thing. Okay? So let's think about it. What does it mean? So what is the most generic situation? The most generic situation is if we take some character, let's call it phi prime, for which the minimum is just a single vertex. This happens almost all of the time, right? But now, if your minimum is the vertex, if you wiggle a bit, the minimum is still the vertex. Okay? So it tells you that for these generic guys, you are in the sigma invariant if and only if some neighborhood around you is. Okay? Now, for the sigma invariant itself, that's always the case because it's open. But minus the sigma invariant, well, the complement is not open, right? I mean, it's not a connected thing. But nevertheless, it is generically open. Okay? So if you take a generic character, and it so happens that it does not lie in sigma g, then there's a neighborhood of it which doesn't either. Okay? So now, what really happens is that when you start wiggling, at some point, you might wiggle it so that the minimal set will increase. And that's the only moment when you can make a transition between sigma g and not sigma g. So it means that the picture you get is, well, I mean, it's determined by this polytope. That's what it means. The only breaking point, if you put the origin of your vector space inside the cube, and you think of cones on over various faces, the transition between sigma g and not sigma g appears exactly when you transition from a bigger face to smaller, to bigger, and so on. Okay, so that's the determinant. Now, I said that we also get this determinant in the n equals 2 case for any, not even automorphism, for any injective homomorphism. Here, the situation is a bit more complicated. Okay, so first of all, we don't get a single polytope, but the different set of polytopes. So we play the same game, but on both of them. So we say that you have to have the same minimal phase on one and the other. That's still reasonable. The bigger problem is that, unfortunately, the choice of the polytopes changes as we change the character. Okay, so as the character travels around, we might have to change take different representatives of the polytopes. That's okay, so I have 2 minutes, and in the 2 minutes I wanted to mention the thing that I think it might be of some interest to some people. So how is it all really, so we have this funny relationship between the Alexander norm and the Thurston norm, which seems to be not only in the three-manifold world, but also outside of it. Why is it the case? Well, the whole point is that it comes down to matrices over group rings. Okay, matrices over group rings. What else? Now, if you have a matrix over a group ring, the G, you want to take the determinant. So what can you do? There are at least 2 things. One thing is that you can map G to G abelianized. Let's say take the free part. This way, you have a matrix, M prime say, which is just the image, inside. Well, it's a matrix over an abelian group ring. Well, an abelian ring. If you have a matrix over an abelian ring, you can take the determinant. This is the Alexander method. That's precisely what it is. The other way is to embed it into a skew field and take the Dieudonné determinant. That is the Thurston method. Okay? So the difference between these 2 is the different way of taking determinants of matrices. And now what we would really like to have is, so you have these 2 different methods. These determinants live in kind of completely different worlds, right? One determinant lives here. The other determinant lives in this G, except it's the abelianized, who cares, right? But you can perform the polytope trick in both cases, as we did. In one case, you get a polytope which gives you the Alexander norm. In the other case, you get the difference of 2 polytopes, okay? You get the denominator and numerator, you take the difference of the two polytopes. I would really love to have a general theory which would allow us to compare these polytopes. By which I mean, the polytope we get here is, say, P. The 2 polytopes you get here are Q and R. How about I move the R to the other side? I use the Minkowski sum, and I want to compare these. Is one contained in the other? That's a question that I cannot answer. I think Florian cannot answer either. Good. So nothing changed. Well, bad, because the point is that if you knew this, then you could get this theorem about Alexander norm and Thurston norms for all Fn ascending Hn extensions of 3 groups. It would give some kind of theoretical reason why it is the case. So even though we've made this observation that it's just about the different determinants, this is not how we actually prove the theorem. Okay, thank you. I don't think I can say anything. I can even the simpler questions that I cannot answer, but maybe you can. So, for example, take a matrix over some group ring, and you compare it to the abelianized version. So, like here. Well, it's just the same setup. If I know that after abelianization, if I take the determinant is non-zero, can I be sure that taking the determinant over dg is non-zero? So that's, I cannot even answer this, right? So that's somehow a very basic step. No, 0 means 0. 0 means 0. dg contains 0. I mean the polytope to be empty, right? I mean 0. Sure. Sorry. So F2 generated by AB, and your automorphism F takes A to B and B to A. But that is clearly polynomially growing, and the image is not input. But its power is second power.
Can you give an example?
I can think about it. Well, sure you can take this and add more generators and do something polynomially growing, but unipotent on the rest. Sure.
Do we know other examples of group that does not come from 2 manifolds but satisfies
the star? Sure. That's a beautiful thing. So That's really, really nice. So how about you take any group you fancy, which just has a finite k by 1, k h1. Okay? Then you know, you take any automorphism of H. What you know is that this group is L2 acyclic. Now, if you took H also to satisfy the Atiyah conjecture, then I guess this does satisfy the Atiyah conjecture still. And now you have to worry a little bit about the vanishing Whitehead group, but the conjecture is they all vanish, so let's not worry. And then you can apply this whole machine. So this is a machine which tells you things about automorphisms of groups in a really large generality.
You think it will always be semi-norm?
Yeah, I don't know. I dream that it is always the same. I have no idea. I don't know. No, we don't have an example.
In your constructions, you apply always to the class time space. It seems to be finite k1 condition. But not also apply to other L2 cyclics, but not.
I mean, so the universal L2 torsion works in a higher. I mean, in general for GCW complexes, right? Finite. Or we've never tried. I mean, it's hard enough to do it on these, so I don't know. Yeah.